So, hi guys, welcome to the like a short intro to GANs, and then we'll go on to homework by Bootcamp. So, to first go on to what GANs are, I'll just share my screen, and we'll be using the slides from the previous semesters. Since you guys are actually from homework 5, uh, you would have actually gone through the slides from the previous semester. So, just let me share this. Can you see my screen?
Yes.
Yes.
Yeah. Okay. So just a refresher about what GANs are. So GANs are a part of generative networks. So you must have actually seen VAEs. VAEs are good for generating new data. They use reparameterization trick so that the random vector is actually from a distribution. But what something VAEs lack is basically a tendency to evaluate. How would you actually evaluate something which is generated by VAE? You can't just eyeball every image or every data which is generated, right? So for that case, we can actually use GANs. GANs have two networks. One is the generator and another is a discriminator. Generator can be a normal VAE or any kind of network which generates data. So if you take a random vector Z from a probability distribution and feed it to the generator, it generates a generated data X hat. And the role of this discriminator is to just identify if this data is fake or real. You have a set of real data from which you actually want to generate new data. So that's the real data distribution. So like, for example, in this slide, if we have a bunch of images, your task is to like model a new GAN so that it will generate another new image, which is very similar to the data which you actually have at hand. So what basically GANs do is they actually model the joint distribution P of Yx rather than the conditional distribution. Conditional distribution is when you have a data X and you find the decision boundary so that the data is separated, like different data are separated. It works for a classification problem. And for generative models, you find the joint distribution. So that's the like basic intro about GANs. And you must have actually gone through the lectures for the quizzes. So going on to some other aspects of GAN, generator is basically any kind of network that generates new data. And the goal of the generator is basically to generate new data, which is similar to the some data points from the actual distribution. So the distribution of the generated data should actually match the distribution of the true data. That's the original goal of the generator. So that's what is required. And the discriminator's aim is basically to identify if the input given to us is fake or real. So the real data is the data which you actually have as training, and the fake data is the data generated by the generator. So that's how the discriminator should work. And these are some math which is not required for now. Yeah, first step for any GANs you must have known is training the discriminator. You have real images from your data set and you have fake images from the generator. So the first thing is that it has to, the labels for the real images will be true and the labels for the fake images will be false. So we'll go to this slide. This will be a little easier to understand. Yeah, so this will be a little clearer. So the objective of your discriminator is that the discriminator should output 1. The actual output of the discriminator should be 1 when the data given to the discriminator is the real data. So X is the real data. G of Z. Z is basically a random vector. So generator of Z is the fake data. So if real data is given to the generator, it has to output 1. That means that the data which is given is real. And if you give the generated data G of Z as the input to the discriminator, it should output the value 0. That means the data which is given as input is fake. At the same time, the object of the generator is that whatever whatever image or data it generates should become close to real. That means it has to fool the discriminator such that the data given by the generator should out data given by the generated by the generator, if given as the input to a discriminator, should produce 1. So the aim of the generator is to produce data in such a way that the discriminator is fooled. So this is basically the optimization problem which we'll be working on in like pretty much every GANs. So before that, we'll actually go on to an example, an implementation example of GANs. I'll share the notebook with you guys. So a little different from what was done in the previous semester, we'll be focusing on like generating art with the help of GANs. So I took this reference, PyTorch tutorial reference to model a DC GAN. So you can take a look at this link. And we'll be using data from this Kaggle competition, which has a lot of Monet images. So the art images. So that's what you'll be doing. These are the basic imports and Kaggle data download commands, which is very familiar with you guys for you guys. So these are some helper functions to unnormalize images. So we'll be normalizing the images in this range with mean of like 0.5 and standard deviation 0.5. These functions are just to like reverse the normalization process. This function is to just show the images. You have global configuration. These are like pretty basic stuff. You have a data set here. So before going into that, so the data which you get downloaded from the competition is something like this. In these 4 folders, we'll just be using Monet JPG. It has around 300 images like of Monet arts. So we'll be taking this as the input data, and the aim of our model is to generate a new image which is very similar to how it would have been drawn by Monet. So that's our goal. You have a set of training data, which is Monet images, and given a random vector to your GAN model, you want to generate a new image, which is similar to how Monet would have drawn. So that's the goal. So you have the dataset class to include the accept the dataset. You have you can use a few transforms like this. I've used 0.5, 0.5, 0.5 for mean and standard deviation, similar to the tutorial which was linked above. You create the data set and data loaders here. And this prints a bunch of training images. So as you can see, these are good art images in the style of Monet. So our aim is to just generate a new image which will be like this. So going on to the GAN models, these are just weight init functions. So this GAN, which was actually followed in the PyTorch tutorial, was a DC GAN. So which takes in a latent vector of like 100 dimension. As you know, the input to the generator is a random variable, as a random vector. And based on this random vector, it will generate a new data. So we give this input to be like 100. This is the constant which they've used. And these are some parameters. NGF is the number of generator features. You can play around with these parameters if you want. So this is basically a generator. At the same time, you have a discriminator as well here, which takes in the image of shape 3 cross 64 cross 64 and outputs a single value, which says if the image is fake or not, fake or real. So fake will get the output as 0 and real images will get the output as 1. So that's the goal of the discriminator. This is how you have a discriminator. So this is similar to like the DC GAN implementation given in the tutorial. And I have actually created this GAN class to make sure that this tutorial, whatever notebook which I'm explaining to you guys, is very similar to your homework 5 notebook. So this is just a wrapper class. This is just to make sure that all the other functions are very similar to how you are going to be implementing in homework 5. So just to make things easier for you guys, these things are done. So, and after this, I've also made the optimizer settings similar to homework 5. So in the tutorial, I think they have used like 2 separate optimizers, not in the form of dictionary, but in the homework 5 notebook, you guys will actually be having it in this form. So we have defined it like this here. So this is a fixed noise vector. The reason why we use a fixed noise vector is that, as you all know, you have a noise vector, you input the noise vector to the generator and you get an image. So if you just have the same noise vector throughout all the epochs, then you can actually see how the generator is generating the same image. So at every epoch, if you want to test out how the generator is generating images, you need a constant set of images. So that's the reason why you just have a fixed noise vector here. You don't want to change it just for the sake of evaluation. And you set real labels to be 1 and fake label to be 0. That's like pretty much standard. And this is the training step of the discriminator, which we'll be doing first. As I explained earlier, the aim of the discriminator is to just maximize this log probability of the discriminator output of the real data and 1 minus the discriminator output of the generated data. So that's what we aim to maximize. And going over this, you get the real data. Labels for the real data is basically ones, because real label is 1. And you get the output of the discriminator, and you get the error. So this error is based on the original label, which is ones, and the real data. As you can see, this is the real data which we get from the function. So that's the log, this term. And now you want to train with the fake data. So you create a noise vector, you get a fake distribution here, fake data. If you pass this noise vector through the generator, you get fake data. And the labels for this fake data would be 0. We are training the discriminator. So discriminator should be able to properly identify between the fake data generated by the generator and the real data which is given to it. So for this reason, labels will be zeros here. And with 0 labels and the output of the discriminator from the output of the discriminator given the fake data input, you get the error, and you just backpropagate both the errors like this. So this, and then after that, you just set the optimizer for the discriminator. So this is basically how discriminator works. You first train on the, you get the loss for the real images, and after that, you get the loss for the fake images, backpropagate it, and set the optimizer. Now, the next step is to train the generator. So both of them trains at different steps. You don't step the optimizer at the same time for both. First, you train the discriminator, and then you train this. First, you train the discriminator, and then you train the generator. So for this generator step, you basically call model 0 grad. Yeah, I wanted to explain this. You can either call optimizer 0 grad or model 0 grad. Some people prefer model 0 grad because it makes sure that everything inside the model, the gradients are 0, but anything is actually fine. Like both are totally fine. So this is a different implementation. That's all. Now we are going to train the generator. So as mentioned in the slides, the object of the generator is that whatever the generator generates, that output should be classified as 1 by the discriminator. So you have the labels to be 1 here. You fill it with real labels, which is 1 basically. You get the fake vector which we have it, right? So the fake images which we use for discriminator over here, and you pass it through the discriminator to get the output because of the output from the generator. So for this, the labels is 1, because in this step, the output of the generator are real outputs. That's the goal here, right? The generator aims to fool the discriminator. And you calculate the loss based on this. You backpropagate the loss, and you set the optimizer. So these are basically the 2 steps in GAN training. This is a training code which I have provided here, and this is how you can actually run this code from on your own. You don't have to modify anything. This is just a simple code to make you guys understand GAN a little bit better. So in the first epoch, you have random images, which is basically from an untrained model. As the epoch passes by, you get the better images like this, so on. So, And the reason why we used a fixed noise vector here is that if you analyze this code, this training code, this the images which we get from the generator are because of this fixed noise vector. So that's the reason why we are actually able to observe how the same image changes over the epochs. So as you can see, after a lot of epochs, you get better quality images. So this is basically how you can actually use a GAN for art generation. So feel free to like run this notebook. And yeah, the next something which you can actually try with GANs is that you can use homework 2 data and generate new faces if you want. So that's something which you guys can try out. So do you have any doubts with GANs for now? Like just the basics of GANs. After this, we'll go on to homework 5. Okay, I'm guessing that you guys don't have any issues with GANs for now. The implementation, like a basic art generation implementation, you can run this notebook to like just play around with it. So moving on to homework 5. So homework 5, as you know, is unsupervised speech recognition. So first, let me just explain what type of GANs you'll be using. You have this unlabeled speech audio, which is very similar to like how you used in homework, the other homeworks. So you have this unlabeled speech audio, and you have a corpus of text. So you get this unlabeled speech audio. You can't just directly pass. Before that, the previous example which I showed you, you have a random vector. You pass in a random vector to the generator, and you generate some kind of images, right? That need not always be the case. So in this USR, what we do is we pass in speech data, and after that we generate a possible phoneme sequence, so that this GAN can not only be used for a actual generation, but can also be used for a recognition purpose. So you get the speech data, you pass through wave to vec. So wave to vec gets time stepwise representations of the speech data, and after getting the representations for each time step, you can actually do a k-means clustering as shown here. If you do a k-means clustering, features from similar features will be clustered together. So getting those as different segments, you can pass these different segments into a generator. So basically, you are taking this unlabeled speech audio, you are grouping it into segments, and then passing it through the generator to get a probable phoneme sequence. That's the aim. So get a good representation of the speech signal, and then try to find a phoneme sequence. So that's what you have been doing for homework 3 also, right? You get a speech signal, you get the output is a phoneme sequence. So how do you actually train the discriminator over here? You have unlabeled text. This is a corpus of text like phonemes. Phonemize is used to like make it into phonemes. This has no relationship with the data which is given here. So like there is no link between them. What the discriminator needs to know, it needs to like learn a distribution in such a way that needs to learn the distribution of this unlabeled data, so that the objective of GAN is that you get a phoneme sequence by the generator. This phoneme sequence should fool the discriminator in such a way that this phoneme sequence should be identical to whatever has come from this given distribution. So that's basically it in USR. And moving on to the handout which we have provided. Yeah, can you see the handout?
Yes.
Yeah.
But before, before that, do you guys have any issues with whatever we have actually seen until now? Okay, I'll take that as a no. Then moving on to the handout. So this is the handout, which this is the training notebook which we have given. So you are free to install other libraries for logging and stuff. Kaggle commands needed for like downloading the data. The first to do is just to like go to your directory. And here, what you need to do for this cell, you just need to go to data sets. Not data sets, sorry, it's task. This unpaired audio. Okay, it's already given here. So you just need to replace these paths with where your data is. So that's what you actually need to do for this node, for this Python file. Then moving on to training again. Yeah, okay. So cool. So the next one is your you have set up the data now. You have set up the data. The next one is to get the data loaders and everything. This is very similar to how you do it for all the other homeworks. You are free to like change all the parameters of the data loader and everything. You don't have any to-dos here, so you don't have to worry about it. Next is the important part. You have the model. Let's get into a more detailed explanation of the model. So if you actually go through this wave-to-web U Py file, the first thing is the config class. So these actually have all the specific config of the wave-to-web model. You need to do a lot of ablations and document your results for the final report. So I suggest you guys try changing these configs. You can actually add or not, like it's very easy to add. They have used something called spectral normalization also, which is default false. You can try it out for true. You can try changing the dropout values and so on. You can use this for a set of the ablations which you guys need to do for the final report. We score based on how you have actually done your ablations as well. So moving on to the discriminator. The discriminator is basically a 3 convolution layer network in this wave-to-web. So which takes the speech audio, which takes the phoneme sequence and tells if it's fake or not. So as shown in the previous diagram. So it's a 3 convolution layer network. And you can try changing the number of layers for your ablations. You can try all sorts of things, and we encourage you to do that. The generate, you don't have any to-dos per se. You can do a lot of things if like to try out your ablations. The generator is basically a one layer convolution at con 1D layer. So that's pretty simple in this. So you can also try adding more if you want. So this is the final wave-to-web model. The discriminator and generator are called here. So the first to do is for you guys is to, in this file, is to do gradient penalty. So go through the paper, use this repository as a reference, and try to understand gradient penalty and try completing it. That's the first to do which you will be having. And the next, then there is also another to do at the bottom. Yeah, smoothness weight. There's also a small to do here, which you can actually go through the paper again and have this repository as a reference and complete it. Then, yeah, this is basically it for this section. And here you need to define the yeah, sure.
In the smoothness, I see in the original code there's another part like calculating the
yeah. I think I replied to you on Slack itself. It's that's not required. Don't worry.
Okay. So
yeah, that's not required
here. Okay.
What?
We don't have to copy that here.
Just no, you don't have to. Yeah, you don't have to. That's not required.
Okay.
Yeah, that's not required. So, any other questions about wave to web Py? Okay, cool. So next you define the optimizers. So you can actually define the optimizer based on these configs. So just a minute. So yeah, there's actually a config file over here. Just a minute. I'm trying to share it. So this is the config. So you just need to find out what config optimizers they have actually used here for the generator. You just need to use the same configuration. That should be more than enough for you guys. So you can try using schedulers if you want. So and try to use mixed precision training. That will actually speed up your training. So next comes the most important part of this notebook is the run model. So we'll go over in detail. So first thing what you can try to do is try to have a sanity check loop where you print whatever is actually there in the in this net input. So you'll get an understanding of what is actually there, what needs to be pushed to GPU and so on. So try to do that first. And after that, in model training, first you need to step the train the discriminator, and then you need to train the generator. So we have put here that you need to use discrim step, right? So let's see what discrim step is actually in this wave to vec. Yeah, if you can see this, so discrim step returns a Boolean value like true or false. So based on this is basically the epoch number. So based on this, or the updates number, if I'm not wrong. So based on this, it will return a true or false value. So if this is true, if discrim step is true, then there is another part in the forward. This is actually called like the model forward. So D step is called here. So based on the update number, this will return true or false. So if it returns true, then that means it is the step for the discriminator. So this part of the code will be run, which is basically training the discriminator. The loss for the discriminator and generator are actually given here. So if this D step is false, then that means the generator is run. So you can actually use discrim step function from the model, and based on this, you will have to step your optimizer, not step. You have to zero grad your optimizer. If the discrim step is for the if this discrim step returns true, then you have to step the optimizer of the discriminator. Else you need to step the optimizer. Not step. You have to zero grad the discriminator optimizer. If it returns false, you need to zero grad the generator's optimizer. So you need to do that. So that needs to be done. So that's how you can actually use discrim step, because I think a lot of people might have faced confusion with this. So that's how you have to use it. And yeah, you get like loss stats as a dictionary, right? So this is basically how you are going to be returning the dictionary. You have losses over here like this. Some losses might be none, some might not be none. You have to accumulate the loss. So if the loss is not none, you can just add it to the total loss. So that's the aim of this to do here. So you have to like iterate through the loss stats in dictionary. If the loss is not none, then add it to the total loss. That's basically it. Just a few lines of code. And this also helps you to get which model is actually trained now, if it's the generator or the discriminator. So based on this group, you update the you step the optimizer, the whether you need to step the discriminator's optimizer or the generator's optimizer. So that's basically it for this code. And these codes are just for you to accumulate these statistics. You can do it even without the stats. You have to just print like the corresponding like evaluation, which loss you want to monitor from loss stats. So that's basically it. For the validation step, the this task.valid step returns like validation loss stats. That's also a dictionary. It has a key called edit distance, so you can use that, because we'll be using edit distance or the Levenshtein distance for evaluation. So you can actually use that in this. So here, I would suggest you to save the model because you need to run for at least 2000 epochs to get a good score. But don't worry, with mixed precision training, the epochs will be like 30 to 40 seconds at max, even with the Tesla T4 GPU. But what I have observed is that your model will stay at around, it will start with around like 100, 150, not 150, 115 Levenshtein distance, and it will kind of stay the same. Like it will be oscillating in 100 and 150 for around 500 epochs, 500 or even 600 epochs. Then after that, it will actually start to reduce. So don't worry, just give it time. I would suggest you to like complete everything, complete all the other parts of the code like as soon as possible, and just allow your model to train. But as I told earlier, it will take a long time. Convergence will, you won't get a proper Levenshtein distance even after like 500 epochs. You'll have to wait for a while. So it will be oscillating until 500, 600 epochs. So just be careful about it. You can actually log the validation training stats also in 1DB if you would want, or you can actually use it in, you should use a different platform also. So we have actually given a code for the test loader here. So here you have a test step function, which is basically, just a minute, is very similar to the valid step function. Yeah, where is it? Yeah, this valid step function, right? So you just need to take a look at this function and modify it in such a way that it works for tests. So remember that you don't actually have labels for tests. So you'll just have to like modify it accordingly. So take this, modify it, and just use it for the test step. And all the other codes are kind of similar to the other homeworks, and you just make a submission, create a CSV, and make a submission. So this is basically it for the handout over here. And do you guys have any questions about the training file, the Python notebook or the handout?
Yeah, I have a question.
Yeah, sure.
So in the part of the run, in the function of the run model,
Yeah, okay.
after if model training, we have the first to do that we have to use the zero grade. But
Yeah,
and we said we can determine whether we have to zero grade the discriminator or the generator based on the discrete step. But
yeah.
why can we use the group variable like you define later, group equals to model.get
Yeah.
for
Yeah, you should be able to. I think I replied to you on Slack also about this, that you can.
Yeah.
So usually I use this because it's kind of very similar to the implementation, I suppose. But this can also be done. This should also be done. Just a minute. Yeah, I think you can also use that. But if you get any issues with this, you can just go back to this. Like anything works.
Okay.
Yeah.
And do we have to import another like the love and distance?
No, you don't have to. You don't have to. You don't have to. So everything is actually taken care of it in the imports itself. You don't have to do anything. If, like, for example, I ran it in Colab for training and everything, so that was enough for me. If you're using a different instance in AWS or something, you might need to install a few packages, but I'm not really sure about it. But yeah, you might have to, but FARSeek should actually be having everything which is required. So that's why we have pip install FARSeek, right? That should be having everything which is required.
Okay.
Any other questions?
And you said in the test part we have to delete the label, but which variable is for labeling?
You'll have to like go through the test valid step and just understand it and do it. It's very similar to it. The test code is very similar to it. So yeah, I can help you in Slack if you want about like going over your code.
Okay.
Yeah, if that helps. Like not here, but yeah. But
Okay.
I can just say that this test step is very similar to like the validation.
Yeah. Okay.
Yeah. Any other questions?
I don't have. Thank you.
How
I don't
about the
have any
others?
questions. Yeah, I don't have.
Cool. So that's about it for the handout. So just be aware of the fact that this just accounts to like 25% of your grade. So your Kaggle submission is just 25%. The final report has around 50% of your grade, but we are actually deciding on the fact of whether asking you to present a small video also, which is very similar to how the project presentations are done. So we'll give more information about that. But make sure to do a lot of ablations, because you need to be explaining all the ablations in your final report, and that carries 50 marks for now. So you need to be doing a lot of experiments with your teammate, and you have to like explain all the experiments in the final report. So that carries a lot of mark. Even though this is just 25 marks, this will actually help you to get those 50 marks. So that's about it. So if I'll just stop recording for now. So, just a minute.